Hey, thank you everybody for joining Rath Associates. We're putting on one of the first. We've been doing a lot of webinars, 20 minutes. This is a PDH credit. Please, for those of you engineers, you need your PDH credits. If you haven't done so already, please let us know all your pertinent information so we can write up the certificate. And if you need it, please send it to support@rathasos.com. And if not, you have our number 631-822-1200. Reach out and we'll get it set up. So thank you for joining us on this webinar, PDH. Because of our pursuit of Local Law 97 and carbon reduction energy savings, we looked at trying to put in Psychometrics presentation. Klas was nice enough to do so. One of the things that's going to be a thread in this thing is that when you're looking at Psychometrics, some of the important things is trying to right-size systems and the use of conserving energy to that end. So with that, we'll let Klas pick it up and take it over, Klas, and introduce yourself, and let's get it rolling.
All right, sounds good. Basically, this was given at a national ASHRAE summer meeting in Nashville, and it was entitled "Avoid Mold and Get Gold." This title was actually copied by the American Medical Association, pure plagiarism, but I take it as a compliment. I've been involved with all forms of engineering. I'm a registered architect, a professional engineer, and a certified energy manager. And in 2012, I got the first ever existing building Emmy from Urban Green and USGBC for taking the world's largest industrial complex net zero. So not a bad background. I've been involved with authoring ASHRAE handbook chapters. I've done 2. Owning and operating commercial buildings. I also rewrote the chapter on air energy recovery. And most recently, I wrote an ASHRAE standard along with other contributors from leading manufacturers across the United States like Munters and other experts in the field on testing direct evaporative cooling. And that's kind of apropos for what we're doing today. What we're going to do is we're going to look at building system and actually a engineering project I had where things were not going as expected. It was a $21 million renovation, and quite frankly, the paint was peeling off the walls 6 months into it. Now, what we're going to do is we're going to talk about the case. We're going to get into some psychometrics, and then we're going to tie it together with peer-reviewed ASHRAE handbook chapter references and pull it all together. And towards the end, I want you guys to solve the problem. So this is a very peer-reviewed presentation that's been reviewed at a national ASHRAE meeting, and then we've used it, and it's been certified for engineering and architectural continuing education credits pretty much all throughout the US. So the base case study is actually a very high-end country club. All equipment was working as designed. It was determined that the design met code, and all equipment was performing properly. A lot of times when I give this presentation, people come up with their own theories that it's the thermostat or it's the location, or no, everything was fine. Top-notch equipment, and everything was working exactly as designed. I think the best way to present this is be careful of what you ask for. You might get it, and that's exactly what this is. Now, the interesting thing about this is we're going to find out that for HVAC and doing sensible air ratios and humidity, dehumidification, typical systems are actually pretty forgiving. You actually have a pretty wide target area to hit. But the first thing I noticed with this was it was a very expensive country club. Membership was over $100,000 a year. It was more like the owner of a company would have membership and use this for company functions, lectures, different things. Very nice club. The occupancy during the week was low. Another way to say that is if you can afford $100,000 a year country club membership, you're probably not playing golf a lot. You're probably hustling and getting projects and extremely, extremely busy. Interesting clue is the electrical equipment had accelerated maintenance issues. They were literally burning out contactors for the motor starters. This to me would indicate short cycling. So maintenance people complained of jammed doors. This was a very nice renovation. It was a complete gut and rehab of a 100-year-old golf clubhouse club member building. Very good food. You go there, you would really feel like you were in a 5-star dining environment. Excellent wine list. Just very, very nice. Probably one of the nicest working environments, except for the peeling paint. The 19th hole was a bar, and it had very nice interior wood finishings, and they were swelling to the point where the door would jam. So there were definitely issues. So chronic comfort complaints, people were not comfortable at any temperature. People complained about cold-like symptoms. I did a little research, had lunch in the restaurant, in the club, and great food. But I did notice that when the air conditioning slammed on, it would drive the temperature down below 60 degrees. And then it would slowly reheat, and you'd go through these temperature cycles that were extreme. So we're going to find out a little bit more about that. The thing about this project was they had been stuck with this problem for the better part of a year, and they really hadn't drilled down and figured out what the problem is. So we're going to look at some psychometric charts. We're going to look at how to evaluate conditions, and then we're going to take it back with microprocessor-based monitoring equipment, download the data, and we're going to actually take a look at what this equipment is doing. So why did all the people have the same complaints, which has a tendency to give a lot of validity to what is at hand?
Hi, Klas?
Yes, sir.
Hey, it's Greg. So I'm getting a lot of, so I saw one person sent in just a note to us saying that he can hear us, but then I've heard a couple people saying they can't. So that's obviously a little concern since we're a couple minutes into this. Can you try on your keypad pressing *1 or #1? And if anyone else can hear us, please let us know.
Let
me.
Yeah, I mean, people can hear you. Click.
So some people can hear us, and some people. I am seeing a lot of people saying they can hear us.
All right.
Okay, sounds like things are going well. Okay, a lot of people can hear us. So why don't you just continue from there? I don't know why there's a couple people saying that they couldn't hear us. Looks like everyone's good. So continue from where you were. Sorry about that.
No problem. And I think what we're going to do is after a certain point, we're going to open it up to some answers. I'll ask a question, and I want to get some involvement to see if people can figure out what it is. So basically, we're looking at balancing reports, technical reviews. Is there something wrong with the equipment? So now we're going to get into looking at the psychometric processes. For some of you, this is going to be just a comfortable review. For others, psychometrics, a lot of people find it to be a handful. If you pick 2 parameters, I think the biggest component of working with a psychometric chart is pick 2 parameters you can work with. I like grains of moisture, and anybody that generally designs for dehumidification is going to work with grains of moisture, and then the temperature on the bottom. So temperature is straight up and down. The diagonal lines are going to be dew point, a little bit more counterintuitive. But if you go for grains of moisture and you do enough of this, you're going to realize a pretty humid stuff is about 160 grains. Bone dry in the middle of the winter. Manitoba -40 is approaching single-digit grains. There's 7,000 grains in a pound. So you're looking at a ratio of about something on the order of 180 grains, 150 grains to 7,000 grains. And from that, you get humidity ratio. I like working straight with grains and then coming over in a temperature, and it gives you a point. And then looking at this chart, once you get to that point, this will be about 50% relative humidity. So here, we've got the rooftop equipment, and the concern is moisture. So what's happening? If you look at a cooling coil on a single pass, it's going to be sensible until you start approaching 80% relative humidity. Then you're going to get condensation. It's going to drip like water dripping off a cold can of beer in the summertime, and it's going to go down. And what happens here is, if this is introduced into a space, you're going to get very high relative humidity. What does that mean? Well, we're going to see later on in the literature, it's predictive that you're going to have hygroscopic effects, which things like plaster, wood, Steinway pianos, they all have an affinity for moisture. If the relative humidity in a space gets to a certain point, the wood will actually absorb water and swell. In this case, they don't like that, because when you're trying to get into the 19th hole, which is a very nice English modeled bar, sometimes you can't open the door. So here we'll look at sensible heating, and here you're just coming back in a straight line. You're not changing the moisture in the air per se, it's the same grains of moisture. You are changing the relative humidity, which is simply the ability of the air to hold water relative to the maximum amount of water it can hold. So if we start here and we're somewhere up around 50%, if you drop the temperature, the ability of the air to hold moisture drops, and so does your relative humidity. So here we're going to look at evaporative cooling, and this was really the way we cooled back in the 40s and 50s. And here you're adding moisture, but you're dropping the temperature. And again, this can get very, very uncomfortable. And the way we solved that back in the 50s, we would use plaster lath and a lot of masonry, and it could handle very high relative humidity. Nowadays, with modern construction, which is less expensive, this would be a real problem. And then we can just take a look at sensible cooling, where all you're doing is dropping the temperature, but you're not dehumidifying. As you drop the temperature, the relative humidity compared to what the air can hold goes up. And here we're doing humidification while heating. So all these different things are combined, and when you look at it, this is really how we're going to solve the problem of what's happening to this country club, and why a $21,000 renovation is having the paint delaminate less than a year after the remodel. Now, the interesting thing is, a lot of manufacturers, in order to increase their EER for split systems, the least expensive way to do that is to get rid of the ability to handle dehumidification or latent cooling. So that's a challenge that we're going to see more and more. So here, we're just doing dehumidification. We're not changing the temperature. We're just simply dropping the moisture content of the air and keeping the temperature the same. Yeah, sure.
Hey, I'm sorry to interrupt you. Can you go full screen? A couple people have asked because I think they're having a little problem.
Yeah, I just did go to full screen. It was part screen. This is full screen.
Gotcha. Thank you.
So now here we do air mixing, and we're taking outdoor air, and we're doing something close to face and bypass. So what we're going to do is we're going to bring in outdoor air, which has a lot of water in it, or it's fairly humid, and we're going to mix it with relatively dry air. And if you do it in the right ratio, you end up with something that's actually pretty pleasant. So the standard that we're trying to meet is ASHRAE standard for human comfort, ASHRAE standard 55, 2019. And basically this gives us a target range from 68 to 78 degrees Fahrenheit and 30 to 55% relative humidity. So in this environment, it's really kind of wet and warm outside, but you're dropping it and mixing it with relatively dry cool air, and your resulting air mix is fine. You're going to be well within the standard range for ASHRAE 55 for human comfort. So this is meeting the complaints of the people in the country club that says they're cold and clammy, and this is a nice predictive way to do it. Now, a lot of people, when they're looking at the psychometric chart, they try to do too many parameters. And typically, I like to do grains and just temperature. You can do dry bulb, wet bulb, very comfortable with that. Or you can do dry bulb and relative humidity. But pick two, and then kind of work with it from there. ASHRAE's got a really nice program for this where you can plot and you can play with the different lines. As a side note, we were doing some runs for equipment up in Northern Territories, Canada, think like Yellowknife, and the moisture line was down on the very bottom part of the psychometric chart, and we thought it was a software glitch. And it turns out that if you're in Northern Territories, Canada in January, you are at minus 40 degrees, and that's the definition of instrument dry air. So basically you have no moisture in the air. You're actually like down at 0 or 1 grains of moisture. But if you think about it, at minus 40, you really shouldn't have any water in there. So now for the initial site visit, air felt cold and clammy. It was a really nice day, 81 degrees, 42% relative humidity. Everything's working fine, and we find all these issues. And my sneaking suspicion was that something was happening when people weren't there. When we actually tracked it, it was something that was occurring all the time. So when we look at all these building issues, the one big clue is the ratio 1 ton per cooling, 80 to 150 square feet of floor space. I typically, if I'm looking at a commercial building and I'm trying to get my arms around what's going on, I'm expecting that number to be closer to 500. So that's one of the components. And we'll ask some questions in a little while. So what we did next was we installed solid state mini computers that had hysteresis and could log the temperature and the relative humidity. We also had CO2 sensors, and we could look at what's happening over a period of time. And if we look at the different areas, outside it's 41% relative humidity, mild temperature 81. Front entrance was at 61% relative humidity at 71 degrees. The lobby was at 76 degrees and 70.4 degrees Fahrenheit. So that's really too high. That building issues are going to occur with building materials. And then when we looked at the moisture content of materials using a moisture sensor, we found that the drywall and the wood trim, they're really, basically you average this out, you're a little over 10% moisture for the different building materials. At this point, you're going to have swelling, you're going to have delamination. So everything is kind of working out. And here, if we look at the ASHRAE fundamental chapter 23.13, thermal and moisture control in insulated assemblies, we see that it's predictive that if you're up around 60% and you go up, the absorption, deabsorption, or the equilibrium moisture content of the materials is going to be a little over 10%. So this is really dovetailing pretty closely to what we're finding. And then we look at the indoor air quality, which is really good. You have very low CO2 rates, which in my mind means that you're overventilating. And the evaluations of carbon dioxide, I would say that you're allowed to be 700 parts per million over ambient. So right now, the last place in the world that saw 400 parts per million was the Keck Observatory at 13,000 feet on the big island of Hawaii with 2,000 miles of Pacific Ocean. So I would present that that probably is pretty good representative of ambient conditions. So by ASHRAE standards, you really could be as high as 11 to 1,200 parts per million CO2 and still have reasonable indoor air quality. So the fact that it's that low means that it's to some extent overventilated. So now the next step is we're going to take a look at the RH microprocessors, and we're going to identify dynamic trends of these moisture issues in the building. And when we look at this, you can see that there's a dead band. And at this point, I'd like to open it up and get some comments from the participants about what they think this represents. And when they're looking at the relative humidity and the temperature fluctuations. So the relative humidity in here is the blue, and then the green is the temperature. So Lou, could you switch it so some attendees could make some comments?
Yeah, I see Michael Ward has his hand up. Michael, did you want to ask a question? Mike, are you there? Okay, just if anybody else has a comment or question, I'd like to respond. All right, I don't see it, Klas. Let's keep it rolling. We'll pick it up at the end, and you can save the slide and come back to it.
All right, that sounds good. So what we're seeing here is we're seeing an awful lot of deadband, and what I believe happened was that as they're trying to make this HVAC system run or function properly, they're creating a larger deadband on the thermostat or the controls, so that the HVAC equipment has a little longer runtime, so it's able to do a little bit better dehumidification. Unfortunately, looking back at the psychometric chart, if you cool very quickly and then you really don't have enough runtime to let the coil wring out the moisture, two things are going to happen. One, you're not going to wring out that much moisture, but any moisture you do wring out is going to have a tendency to be reintroduced into the airstream. In other words, if you keep the air flowing and you're blowing across the coil, you might condense out some of the water, but eventually with continuous airflow, you're going to have a tendency to put it back into the building envelope. And that's why the relative humidity was going so high. So here, for a single pass, the equipment, and this was pretty much coming right off the manufacturer's data, this is what it predicted to do. It would overshoot the target temperature, and you'd end up basically providing supply air at 100% relative humidity, which is wet, and you'd be at a fairly low temperature. It was predicted that this would bring in the air, run for a couple minutes, and bring it down to 100% relative humidity and 55 degrees, which is what caused the cold, clammy feel. So now we're looking at entering air and the RTU, and we're looking at the scope of the HVAC problems. HVAC system is very expensive to operate. A lot of the rooftop equipment was 10 to 20 tons. When I sized this equipment, I found that a typical sizing when it's unoccupied would have been something on the order of 1.5 tons to 2 to 3 tons per space. So, and these large systems, they're really geared for a crowd of several hundred people. They're going to bring in a couple thousand CFM of outdoor air to try to provide 20 CFM per person. So the problems to solve is the equipment doesn't stay on long enough or have long enough run times on part load conditions. The equipment, because of short run times, does not have the ability to wring out the excess moisture. And the large amounts of outdoor air, even during periods of low occupancy, increase the amount of water and air. So when we looked at this, and I agreed with a consulting engineer who was a member of this club that he met, code required cooling loads for maximum occupancy, but what he didn't address was part load. And given the operation of this facility, 90% of the time, it was really in an unoccupied part load with maybe 5 people in a building that was really engineered to handle several hundred. So the board was all up in arms, and they felt that this engineer had not designed a good system. And I said to them, well, if you could do something that had a payback of a year, would you do it? And they all agreed they would. It'd be their fiduciary responsibility as directors of the board for this club. And I said, well, you got a guy that spends $100,000 a year. I think you could put in a set of split systems that would solve this. And I think it costs something on the order of $80,000. So that would be a payback of something on the order of 9 to 10 months. So that's what they did, and it did solve the problem. So one thing that came out of this was the sensitivity analysis of how much can you oversize the system. Now, a 20-ton rooftop unit is going to have the ability to offload. So it's going to be maybe 2 10-ton scroll compressors, or it's going to be a 7 and then a 13-ton. It's going to be a mixture, but they really don't dehumidify well while they're doing part load, and you're still bringing in a lot of outdoor air. And if it's oversized by a factor of 400%, you're not going to be able to overcome that even with the best controls. So we found that you can have pretty good dehumidification and still be as much as 200% oversized, but you can't be oversized 400 to 500%. And that's what the issue here was. And it wasn't that easy to figure out. It really wasn't. But if you look at all these different parameters and you follow the ASHRAE standards, it is something that you can work around, and you could also avoid it too with a little bit of common sense. Now, the way to really deal with this would be to have energy recovery systems tied to a BMS system or tied to an occupancy sensor tied to CO2, and have the outdoor air intake go dormant when you don't have a lot of people. And then you probably could have made this work with existing equipment. But if you're running 90% of the time under very small part load, there is a benefit to just having a dedicated smaller unit that really is only designed to temper and dehumidify an area. The other thing is it takes a lot less energy. So the final solution was the ability to reheat with an ER unit, reduce supply air, temp and humidity, and replace and install smaller HVAC systems matched for part load conditions. So, and neat club, I still wouldn't pay $100,000 to join, but it does solve the problem of existing buildings. The other way to look at this is if you have a building that has no outdoor air, if it was built just after the energy crisis in the 80s, ventilation standards back at that time did not really require fresh outdoor air. You could meet ASHRAE standards in the 1980s for 5 CFM a person just by envelope leakage and simply by having people opening and closing windows and doors. And that's what coined the phrase sick building syndrome. So if you have a project like that, you could work with the engineers at RATHI, and we could install energy recovery with a CO2 sensor and solve that problem. All right, we'll open it up for questions and answers, Lou.
Okay, thank you, Klas. Let me take a look and see what we have here. One of the questions was, and I guess
I'm sorry, Lou and everyone, just real quick, before we jump into the Q&A, I just want to make sure that we get the answer from everyone and we find out who actually requires a PDH credit. So this obviously, again, is a PDH credit presentation. So anyone who requires one, just to make sure that we get it out to you, please just send in your information here. So everyone just, we're going to leave this up for probably about a minute or so. So make sure you get this in, and we'll get these certificates out as soon as possible. So while everyone's voting on that, is there anything else that you wanted to chat about in the meantime? Doesn't sound like it. Okay.
Let's look at some modeling software. Are you guys up for that?
Sure.
Well, we just while the presentation or the poll is going, that's going to be up on the screen. So we got almost everyone's voted. We got about 70%. So just wait another couple, maybe 15, 20 seconds. Just everyone, make sure you get the answer in, because if you need a vote, if you need a PDH certificate and you don't answer, obviously might be challenging to get one to you. Obviously, you could always reach out to us if we don't get it to you. Best way to reach us is either our phone number or our email, support@rathasos.com. That's support@rathasos.com. So looks like just about everyone has voted. People are still slowly straggling in. I'm going to close it out, though, so anyone who didn't get the answer in will have to address us separately. And here we go. Closed out. Okay, so now everyone, as a reminder, and it looks like everyone has pretty much seen the questions. Everyone was able to reach out and let us know that they were able to hear us or not hear us. And we actually saw a lot of people reaching out while you were speaking with their thoughts on your system. So we don't have, we're not opening up anything for audio. So anyone who has any questions, please address them in the question bar. Send them in, and we're going to go through them one by one. We got plenty of time here, so just fire away. Anything you want to go, whether it be beginner, intermediate, advanced questions. Klas here can really dive into anything. So while those questions are rolling in, Klas, why don't you show people what you got going on there?
All right, so basically this is a predictive model. It's been used for state-approved energy efficiency grants in New Jersey. I think it's done over $20 million worth of grants. It's been reviewed by over 50 utility companies across North America. And really what this is, it's a predictive tool, and it's not like Carrier HAP or Train Trace where you drill into it and you never really figure out how it works. It's pretty much open protocol. So in here, we look at the existing fans, what their power consumption is, the proposed new fans. This could be just one existing exhaust fan, but typically if we go to high efficiency ECM motors and they're tied into a BMS system, it's not uncommon that they use two fans will use a fraction of the power of an existing standard fan. Part of that is airfoil curve technology with the fan blades. But basically we plug in all this, the heating system, the cooling system, the amount of outdoor air, the number of energy recovery modules, and we put all these things in, and we find that we get a very fast payback, and we look at the internal rate of return, and we go through these different components, and we can change this. We can say the avoidance cost is not 14,000. We could take it down. Let's. And then when we go through this data, we basically look at the thermal efficiency of our dedicated outdoor air system, and we go through the bin values for temperature ranges over a year, and we come up with a thermal advantage. This is backed into the existing equipment on site, how efficient the heating system is. In this case, it's 80%. That's real standard. And then how efficient the cooling equipment is, how many kW a ton, or the different components there. And we boil this down, and that's what the issue is. That's kind of high. I'm going to call that 1.4. Hey, there we go. That looks more normal, a 2-year payback. So when we go through this, and if you find that it is a ridiculously fast payback, that does happen for industrials. We did Chanel, the perfume company, there they ventilate 24/7. We had a very nice payback there. It was less than a year. So you look at this, and then we can take it to carbon reduction, NOx, SOx reduced, and the EPA has a standard calculation for the amount of CO2 reduced depending on what part of the country you're in for an average family car traveling 12,500 miles per year. And in this case, for the 6,000 CFM system, it's taking 27 car years off the road. To date, we believe that we've taken something on the order of 800,000 car years off the road. But the interesting thing is, when you take a look at the payback analysis with a 2-year payback, this will give an annual rate of return, and a lot of the older systems now are well over 10 years, and you're in this area where it's basically like printing money. The other thing that we find in industrial applications, it also improves human comfort. So it's not just about saving money, sometimes it's about meeting ASHRAE standard 55. And for Chanel, the perfume company, they had to worry about fugitive alcohol emissions from making Chanel No. 5. And when that hit a certain level, they actually have to worry about lower explosive limit of alcohol in air. So they would pull everyone out in the wintertime and flush the work area with fresh air. And when they came back, it'd be very cold. And they had a huge turnover from this. The HR people were saying that this could involve as many as having to go out and find 20 to 30 new employees every winter. So, but the good engineers at Rathy can go through, do this modeling, and do an economic payback analysis. So, any questions?
Klas, I have kind of a lengthy question for you. It's a 3-parter about the system at the country club.
Yeah, sure.
All right. So the first part of the question is, was any of the original equipment completely decommissioned after installing the newer, smaller DX systems?
No, not at all. If you had 4th of July and you had a wedding at the same time, you actually needed all the tonnage. The problem was you only needed it for maybe 5% of the hours in a year. But there were times where you did need a 20-ton rooftop unit for a 3,500 square foot bar. If you had 100 people in there, yeah, you needed all of those 20 tons.
All right, second part to that is, what disabled the smaller units during an event when the larger systems would be necessary?
Well, typically you could phase it so that you would have the smaller systems come on first and put it into deep setback, and then the larger system would be the actual target temperature with people in it. So you could either do it through a BMS system, or you could have 2 separate thermostats just set at different times. If I look at a bar, or a restaurant, it's not uncommon to have half a dozen thermostats, and then you basically adjust them for what you want. People watching a sporting event in a bar probably are going to want it a little bit cooler than people sitting at a table eating dinner. It's activity driven and what people want.
Understood. Thank you, Klas. And the last part of that question is, can you advise if they have since solved the contact or motor starter issue, assuming the equipment is no longer short cycling?
It did solve the problem. When the equipment was trying, when you had a 20-ton rooftop unit trying to chase a 1.5 ton load, what would happen is this thing would be short cycling. It'd be going off and on like every 3 minutes, literally as short as it could. And in order to make it even run for 3 minutes, they had to make the deadband a lot wider just to allow the equipment to really even come on for any reasonable amount of time. So once the equipment was used for what it was intended for, which was pretty close to full occupancy, then the smaller unit would take care of it. But if you had something in between, you could have people playing golf and, right around 5, 6 o'clock, they start coming in. And now all of a sudden you have a surge. They stay in the bar for an hour or two, the large unit would come on. But it's not short cycling. Then if you've got 50, 100 people in the bar and they're getting ready for dinner, it kind of works. So, but I've seen that problem in a lot of places. This was probably the most extreme.
Gotcha. Thank you, sir.
Okay, I've got another one for you here there, Klas. When the sizing program that you just used, is that something that's available just through us, or can they buy the program? How did they get access to the sizing software?
That would be just through you guys. It'd be right through Rathy. But
okay.
It takes a little bit of training to use it, and it's also proprietary. I mean, that thing will generate some serious grants, so we don't want to just give it away.
Okay, so that is a follow-up question. If they had a few questions on a couple of systems that they need to design with, could we work with you and them to try and work through the selection cycle on this?
Absolutely.
Klas,
okay, another one. Go ahead.
Sorry, Luke. I'm sorry to cut you off. Klas, does using a VAV unit, not necessarily VAV boxes, along with hot gas reheat, where lowering airflow and outdoor air through the system help reduce the overall cooling and mitigate the humidity?
Well, if you have hot gas reheat, now you're giving that internal heat load, so you do give the cooling system a chance to have a little bit of runtime, so it could help solve it. I still think that if you got a 20-ton rooftop unit and the load's 1.5 tons, I think it's just too wide. I think that is 2 separate systems. But they are doing now with the variable refrigeration volume systems, they are claiming that they can really go down to very small part loads, but it's tricky. I mean, the thing is, you want to make something that's going to be reliable, that really doesn't require a lot of tweaking. And when you go too far, too extreme, and the 2 systems worked really well. So having, but this was kind of like a binary point on this place. I mean, it either was jammed full or it was empty. I mean, it really was 2 different HVAC systems. If you're going to go from a bartender and 1 or 2 people to 200 people, I mean, 200 people is a 20-ton load all day long. So, it's very small part loads and then full-on occupancy. I think the way to do that is with 2 different systems. And you could do something very exotic and very expensive, but you got to find people to service it too. So I think at the end of the day, if you do something that kind of fits, I think it just makes the entire project work better and you have happier clients. So just a thought.
Okay, for the rest of you, please keep those questions coming. We see a couple here. If you're approaching a project like this, what's the best way to start with part load design? And should you use smaller, more systems to be like cascading as we would with boilers?
Well, one thing is you don't want to overcomplicate the system either. One thing you can do is, if you've got 100 people, that is going to be a couple thousand CFM of fresh outdoor air. So if you have an energy recovery unit that's upwards of 80 to 95% thermally efficient, you can almost decouple that outdoor air load. That's going to help a lot. And now they do have systems where you have a smaller, you have stage compressors in rooftop units where you could do a smaller one for the part load, and then when you have full-on occupancy, with a proper energy recovery or DOAS system, it would really solve a lot of problems. The big thing here was they had the same amount of air coming in, whether there were 2 people in this bar or different parts of this club, or they had several hundred. So that outdoor air load, even on a mild day when it's, you know, like 42 degrees outside and 81 degrees, when you take that in and you cool that on a single pass, you're just not going to dehumidify it. And the relative humidity is going to go up as you cool it 10 degrees. So all the numbers really fit. We played a lot with the different psychometric charts, and it was predictive that on a single pass, you were really going to end up with very humid air. If you had energy recovery and it was tied either to occupancy sensors or CO2, you could just eliminate that outdoor air coming in, and you'd then just be dealing with recirculated air. I still think a unit that large under that light and occupancy is always going to be a challenge, but I think it would have been more manageable. But at the end of the day, you know, you can sell a solution to a problem if it has energy savings and if it reduces their utility bill. So the net effect is they solve their comfort problems. They stopped delaminating things. They stopped peeling the paint off the walls. The people were comfortable and their energy bill dropped by a couple $1,000s. So, I mean, you know, all the way around, it was a win. And the way that you approach this determines whether it's a problem or whether it's a solution that they're happy with. So in one way, the way you present this, you can present it as a screw up that has to be fixed, or you can present it as a way to save energy and make people more comfortable. So I always like to approach things from a positive standpoint, and it ends up being more successful that way. Everybody wins.
That was a good answer, Klas. And also to follow up on that, and I did some research last night. There was a Rocky Mount ASHRAE meeting where one of the first things they looked at was energy recovery ventilation, which reduces a lot of the loads. So like when we look at the pumps, sometimes you want to look at the pump instead of before you change the chillers, you might look at the pumps and see what exactly the need is so that you don't oversize the chiller. Is that a valid point on this case?
I think it's a very valid point. The other thing is it depends on the type of chiller you have. Like if it's centrifugal, it doesn't do part load really well. Positive displacement chillers do, like scroll or helical rotary chillers. You can really offload and you see the EER go up. But if it's centrifugal, you really want to size the thing for 80% of full load. That's really its sweet spot. But if you offload a centrifugal chiller, you can get really horrible performance, and they will track down to 20% of full load, sometimes as low as 10. But the EERs there, or the kW a ton, are crazy. So it really depends on the equipment. And, you know, if you have a main system that serves the primary function, which is having a large gathering of people, a wedding, and, you know, whatever, it does make sense to really dial that in. And then if it's kind of in deep setback with 1 or 2 people in a building designed for a couple hundred, I like the idea of 2 systems. It kind of works nice. And then they can quickly switch between the 2 as things change. So best of both worlds.
Hey, Klas, here's another question for you.
Sure.
On the order of 10 to 20 tons where dehumidification is crucial, is the best unit selection simply to get a hot gas bypass capable unit?
Well, it gives you the ability to do reheat. And then with that, now you can create an artificial load like you do have 50 or so people, or maybe even 100. So in that sense, it does give you the ability to cool, dehumidify, and keep the unit from short cycling. And you've already got that energy. You're not creating it. You're just dumping it in the ductwork in line with a cooling coil. So, you know, instead of rejecting it up on the roof, you just do it in line. I kind of like that, and it gives you the flexibility to basically do whatever you want psychometrically. So, I mean, that's nice, but it's still going to use a lot more energy than a 3-ton unit.
Okay, Klas, as a follow-up to my last question, the gentleman's doing a design on a facility like an exercise facility at a high school.
Right.
With a system like that, if you're using this an ERV, and there may be a couple of different selection styles out there, but
Right.
with an ERV, if the temperature outside goes down to, like, let's say 10 degrees, is the units, or can the units be adversely affected by lower temperatures?
Well, it depends on the type of energy recovery. If it's, if it's something with a wheel, if it's sensible laden, theoretically, you can form ice anytime you really go much below 30 degrees. If it's fixed plate, like a BPE unit, that will be able to handle down to -20. It has no moving parts. Typically, we go up into Canada and we don't even use a defrost mode down to -20. Down to -40, we do a cycling defrost. But everything has its place. Like a wheel can fit in a very small space. If you have the intake and exhaust in close proximity and you only have a foot to work with, that's a wheel. If you have more distance to work with and you want better thermal comfort, I think at this point we've done a couple thousand gyms and classrooms in central New Jersey in high schools, magnetized schools. There we were able to just put the units up, no heating and cooling in line, just move air out, move air in. And I can actually show a picture of that, show what it looks like. So let me just. So this right here is what it would look like in the ceiling of a gym. So we're going right here between the steel metal trusses crossing the basketball courts, and up here we'd have a 4,000 to 6,000 CFM fixed plate energy recovery module. This is a smaller one, but I mean, it's an option. This is 2 side by side. This is another gym application. And all this is just a very long direct counterflow heat exchanger. And the concept is you take 5 cubes and you rotate them 45 degrees. The micro channels all go out in one direction, and then the fresh air is open plenum. And with this, you can get well into the 90% efficient. And it also has a laden component too. We have little nanotubes at the end of the fresh air flow. So we'll go from the fresh air to exhaust. Interesting thing about that is it doesn't diminish. Like if you have lithium salts, lithium bromide, lithium chloride, impregnated materials, you have a tendency to lose about 1/3 of the desiccant per year. And over a period of 3 to 4 years, your enthalpy device, actually fixed plate or wheel, has a tendency to turn into an HRV. This is actually a mechanical process that doesn't use any chemicals or salts. So we believe that this is a 20-year process. And when I was talking to Fred Turner, the editor, past editor of ASHRAE Journal, he was basically saying that the life cycle that you got to look at now for equipment is really 20 years. So that's part of the ASHRAE handbook I authored, was the life cycle of different HVAC components, chillers, boilers, and different types of equipment. So, any questions?
So I have another question here from you. How did you get fresh air in part load of the bar?
Well, if your part load down to 1 or 2 people, the answer is we were fine with really just not bringing in fresh outdoor air. If you have a 30,000 square foot country club and you've only got 3 or 4 people in it, there's going to be enough airflow just from infiltration. The time that you really need mechanical ventilation, or you need the rooftops bringing in 20% outdoor air, is when you do have, you know, Friday night happy hour or some sort of event, a wedding or 4th of July, and then you mechanically move it in. But if you only have 2 or 3 people in there, you know, like a club manager, bartender, and a couple kitchen staff, you're going to have excellent indoor air quality just from infiltration. The front door of the club, generally, if it's golf season, will generally be open, so it's not a super tight building anyway. But you could add a small ERV if you had some sort of IAQ concern. And the neat thing is, if it's over 80% thermally efficient, you can basically put them anywhere. You don't need to tie it into existing HVAC or other systems. You can basically just plug and play. And that's, yeah, and LEV, local exhaust ventilation, is going to become a much bigger deal dealing with the coronavirus and other things. If you've got something that you can just put in place and pull the air from an exam room or where you're greeting new patients, you can keep that area very negative pressurized, and then you can supply fresh air to where the workers are. So that adds a level of protection or air movement, and then that is going to have a tendency to reduce transmission rates. Nothing's 100%, but generally, if you have good ventilation, we're seeing that from studies coming from China, actually. They did an analysis of a restaurant with 68 people in it, and they had one person that had coronavirus. It was actually the first 10 cases in Godon, China. They would recirculate. They had these 5 terminal split air handlers. All they would do is just take the air from the restaurant, pull them in the bottom, and then shoot them out the top. And the 3 tables that were in line with this one unit, where the one person had coronavirus, most of the people in those 3 tables got it, and it was over a relatively short period of time. So ventilation flow path with this particular virus is a pretty big deal.
Okay, a couple of comments. One is, everybody, we have a few handouts. Don't forget to grab the handouts. If you need anything else, or you have some suggestions for a future PDH course, we have some on boilers and pump efficiencies. Please let us know at support@raftofsos.com. And there is a question here. You do show in your brochure, and not in general for you, but other manufacturers, what are the largest sizes of VRVs that are typically available? And you can address it for yours as well.
Well, there seems to be quite a lot of options in the residential market. Like if you're down around 50, 60 CFM, up to maybe 200 CFM. And then when they get larger, I think the options diminish. There's quite a few manufacturers that will go up to 5,000, 10,000 CFM. And then once you get much beyond that, you know, if you're trying to do a wheel that's very large, it's hard to make it structurally stable and be able to rotate for a long period of time. So once you start getting really large, I think fixed plates have an advantage. BPE can go up to 100,000 CFM with just standard module sizes of 20,000 CFM a module, and then you header them. That's a real standard thing to do, and that probably is as large as these systems get. But if you look at, again, you know, owning and operating commercial buildings, we did the audit of the building stock in the United States. Most of the rooftop units and equipment, I'd say over 90%, are 40 tons and less. So if you look at that, probably 90% of the equipment out there can be handled with anywhere from 2 to 8,000 CFM of outdoor air. And if you need to go up to 20,000, you can. But I think the larger systems are relatively rare. So like this one down here, that's a 4,000 CFM system. and that's going to handle, that'll be half of the ventilation for a magnet high school gym. And in this case, I think it was like 3,600 students. So if they have like a sporting event, like a basketball game or something, they would kick on 2 of those and vent the gym and the spectators.
Hey, Klaus, I got another question here for you.
Sure.
If the building has an expected moderate occupancy growth within 1 year, what's the best way to accommodate this without oversizing equipment?
That's an interesting question. I mean, if it's a moving target and it's changing, ventilation is easy. You just add another energy recovery module, and that'll offload most of the outdoor air. If you have, whenever I do a central chiller, you know, for a private school, I did one down south. It was 2 million square feet of campus and classrooms and different buildings. You want to build in the ability to add additional chillers, and you want, in an ideal world, to oversize the piping a little bit to accommodate the hydronics. I really like decoupled primary secondary loops. So, you know, I give the boiler, the chiller, the flow that it likes, and then I pull off of that loop, and then I go and do smaller branch systems, and I give them the flow they need. So with that, with a decoupled loop, you're not trying to run a chiller or a boiler plant off of the distribution system. And the answer is you can build into it for a certain extent. Like, let's say it's an 8 million BTU boiler plant. If you're replacing an old Cleaver Brooks or Weil McLean or HB Smith or something like that, and you're going with a new modern Lackenbar or something, you're really going to change the footprint. You're going to have something that's the size of a school bus, and then you're going to go back in with modular 2 million BTU boilers that are the size of, you know, basically a filing cabinet. So you're going to have a lot of extra space. The question is, can you get the air out of the mechanical room, the flue gases? Can you pipe for it? And a lot of times you can. So I've done that with historical places, and I do typically try to give them the ability for future growth. And if we can build that in on the front end, it's always nice. Some people just don't want to spend the money. I mean, it depends on your client too.
Okay, Klas, probably a follow-up to that design from the engineers working on that project at the school. Today, energy savings by reducing room sensible heat can exacerbate the problem. And I'll take that as a question or a comment. You can address it either way.
Yeah, one thing is, if you have a heating bill, you have energy to recover. So specifically in one school, Hopewell schools, they would run the heating to precondition the classrooms for students coming in. The school I'm thinking of was 100 years old, had an old steam system. There was no modulation at all. It was like you kick it on, you cook the building, and then the students come in. But by really dialing in the energy recovery, they were able to run the classrooms even down to 10-degree outdoor heat with only the body heat coming off the students. So what this got them was that they were able to run the school basically just by recycling the energy off the population, and just let the steam system idle while people were there. Before, they would adjust the temperature by the number of books they had in a window propping up, and, you know, letting cold air in, and it would cycle on and it'd go to 95, and then they would cool it off. Tremendous waste of energy. Nobody was comfortable. And the teacher said the first year that they went through a wintertime class environment without having a head cold, or, you know, it's not healthy if you really cycle people through extreme temperature swings. But yeah, that's the answer. You can dial in with 90% thermal efficiency and be able to shut off a steam system that doesn't work.
Okay, Klas, I think that pretty much wraps it up for everybody. We want to thank everybody for attending. Please remember you can get questions answered. You have the handout still there. You can get anything from support@rathassoc.com. We all want to thank you very much, Klas, and I'm sure if we have any engineers that needed the PDH, you'll get us the information. We'll get it to you. And if they have any specific questions or comments, we'll relay that to you. Any parting words, Klas?
Well, it's a brave new world. We got to deal with higher exhaust rates. We got to do all this crazy stuff. But the good news is there's equipment out there that can help us do it. So it's getting more challenging. People actually want to be comfortable. And it's a little bit more of a balancing act than it used to be 10, 20 years ago.
Thank you, Klas, and everybody stay safe out there. Thank you very much.
All right. Be well, guys.
Thank you.